Yeah, ma'am, you can start now. Yeah.
So today's class is basically on the history of quantum mechanics and what led to its development. It's called mechanics because it is a full framework, both mathematical and theoretical, which describes systems, specifically quantum systems. And the more important part is to know what the quantum bit is. So what is quantum and what is classical? Okay. So the first thing we'll discuss is classical versus quantum mechanics. Then we will talk about the failures of classical mechanics. Basically, what was it that could not be explained by classical mechanics, leading to the development of quantum mechanics? Then we'll talk about wave-particle duality, which sounds very interesting, and it's also actually interesting. And then we'll talk about the Heisenberg uncertainty principle, which is at the very core of quantum mechanics. So the first thing is, what is quantum mechanics? Then why was it needed? And once you know why it was needed, you will realize what it can do. So what are the success stories of quantum mechanics? And once you know that, you must have some motivation to study it. So the last thing we should address is, what can I do with it? So what remains to be done with quantum mechanics and how it is a tool in the hands of scientists today. And in doing so, throughout the course, what you will realize is the different ways in which you can explain an experimental observation. In most cases, experiments have preceded theory. And then what happens is just 1 minute. Okay, so you will see that experiments have preceded the theoretical developments. And after a theory is developed, if there are some things in the theory which are not, people are not absolutely certain if they are right or wrong. If there is some component of this, then there are experiments to verify these theoretical predictions. But those are much fewer than the experiments which precede theoretical development. Okay. So once an experimentalist makes some observations, then what does he want to do? So he wants to explain these, right? He wants to understand more about the system he is experimenting on. So he first tries to apply existing knowledge. So maybe what he sees is already understood, or maybe that aspect is not understood, but the existing theories, if he applies it properly, he will be able to explain it. So that is the first attempt that he makes. Then if he sees that this is not working, he tries to develop new concepts. So he might try to extend the existing theories, or he might try to make a new model but apply existing physical principles. Okay. Then the third thing I'm saying is, do the math in both cases. So what I mean by this is that for a given experiment, you always have to do your own derivations. Even if you're applying existing knowledge, even if you're developing new concepts, to exactly explain your observations, you always have to work things out, because no theory will exactly fit what you're doing. So you'll have to work out some part of it. Okay? And then this is the math which turns out to be useful later on. So then comes the fourth point, that you use the math to discover interesting implications. So you have made some observation. Maybe that particular observation is not directly applicable, but when you understand why you get it, you come up with ideas to use this in more useful things. Or or you realize a new aspect of the experiment that you can verify, and you design another experiment. Okay, so this is the steps involved in explaining an experimental observation, and it becomes very clear in the context of quantum mechanics. So I wanted to discuss this first. So let's see what we had before quantum mechanics. We had classical mechanics. So by classical mechanics, what you basically refer to is Newtonian mechanics. So what is Newtonian mechanics? It's 3 Newton's laws that you have studied from a very young age. And the most relevant of them is, of course, force is equal to mass into acceleration, or that force is related to change in momentum. Okay? And that tells you that when you apply a force on a system, then it gains an acceleration, and this acceleration tells you the trajectory of the movement. Or even if you don't have an acceleration, Newton's laws, so we might like if you have velocity, for example, then you know the trajectory of the particle. So all of Newton's mechanics is based on the fact that you know the path by which a particle travels if you know the forces on the particle and the initial conditions of the particle. Now, when did this start to be challenged? So there are 2 domains where Newtonian mechanics failed. One is when the speeds of the particles or matter becomes very, very high. So when it becomes very, very high, then the mass is no longer a constant. It has to be modified with a velocity correction, and this is what is called the relativistic correction. So the high-speed domain of Newtonian mechanics is not accurate. You need relativity to address it. The other domain in which Newtonian mechanics failed was when the particles became very, very small. So when particles became very, very small, then what we call quantum effects, so some additional strange, what should I say, influences were observed. So Newtonian mechanics could not explain the behavior of very small particles. But it was not possible to just do a quantum correction. So a relativistic correction was sufficient to address the high speed rate, but the small size could not be handled by a correction. So what happened was that the full mathematical machinery changed, and we came up with quantum mechanics. And when you did that, what happened was that the distinction between matter and radiation, that also becomes blurred in quantum mechanics. This is especially true, you will realize, when we talk about wave-particle duality, okay, in the 3rd part of this subsection. So, but quantum mechanics, you might think, oh my, this is a problem, that if you cannot distinguish between matter and radiation, how do I handle that? But you realize that it actually unified things. So it made, so the more universal a theory, the better a description it gives, and the more applicable it is in all domains. So that is something that quantum mechanics achieved. Of course, we don't have a full universal theory yet. And in most cases, the radiation is still treated classically for simplifying both mathematics and understanding. But in principle, quantum mechanics handles matter and radiation on the same footing. And within quantum mechanics, there is basically 2 subdivisions, you can say. One is statics and the other is dynamics. But these domains are not exactly equivalent to classical statics and classical dynamics, because in quantum mechanics, nothing is ever really static. Okay, so everything is a sort of average picture of changing things. So when we talk about statics, this is mostly in terms of energy. So when the energy of a system is not changing or not under, and the system is not under external influence, that is called statics. And when there is external influence, it is called dynamics. This may not be obvious at the moment, but I'll mention what is statics and what is dynamics as we go along. Okay, so what are the main distinctive features of quantum mechanics? So the first one that tells you that it's different from classical mechanics is that the momentum is not simply a function of mass. The momentum is a more intrinsic quantity in quantum mechanics than the mass or the velocity. So mostly we will keep talking about momentum rather than mass and velocity separately. And this momentum is related directly to the wave nature of the particles, specifically the wavelength of the particles. Then the energy and the momenta are discrete rather than continuous. This is the second salient feature of quantum mechanics. So what does that mean? That means that there are allowed values of energy and momenta, and you cannot change things infinitesimally. There are discrete jumps when you change energy or change momentum. This is what is called quantization. This is the very basis of quantum mechanics. And what this leads to is equations which are probabilistic versus deterministic. So what does that mean? So when you have a deterministic equation, you only have one answer. So given a initial velocity and time and acceleration, you can always predict where a classical particle will be after, say, 2 seconds. Exactly, there is only one answer to this. But when you talk about a probabilistic picture, your answers will have certain probabilities. You will have a range of answers, and each of them will have a probability. You can have a maximum probability, that you can have, but you will have other possibilities as well. Then the fourth point is that the particle trajectories then become obsolete. So if your equation is not deterministic and you don't know from point to point where the particle will be, then you cannot plot a trajectory. You can only have some probabilistic pathways. Okay? And how you handle this is by taking an ensemble picture. So particle trajectories become obsolete, but only the ensemble picture is relevant. So even if you want to know the path of a particle, you will have multiple paths with various probabilities. Okay? And the last point, which caused the most sort of trouble among scientists and was a big barrier to the acceptance of quantum mechanics, was the concept of collapsing into a particular state. So when you try to get information out of a quantum system, whether by looking at it, which means that you shine light on it, for example. So you're trying to get information by probing it with light, or in other ways, the quantum system will then collapse into one of a known set of states. So this is a very problematic thing. So quantum systems have a set of states which are called eigenstates, which are states of fixed energy. We will talk a lot about eigenstates, so don't worry if you don't understand at the moment. Then when you try to find out about the quantum system, then it will always give you one of the eigenstates. So you will always find it in an eigenstate. But in reality, it is not necessarily in an eigenstate. It may have been in an eigenstate, in which case your answer is correct when you observe it, but it may not have been, but you will still get one of the eigenstates. And if you do multiple measurements, you will get various eigenstates with various probabilities. And you have to sort of construct back the original state from this understanding. It's not like you look at the system and you know, okay, this is its mass, this is its velocity. It's not like that. So you will get different answers if you repeat your measurement. Okay. So this had great difficulty in finding acceptance among scientists. As you see, I mean, even in all of your minds, it must seem strange that this is happening, right? However, some classical concepts they carried over to quantum mechanics, such as the virial theorem, which is the fact that the ratio of the average kinetic energy and potential energy is a constant characteristic of the system. So in classical, this is a classical concept, but it became a very important fact to verify for quantum systems. Okay. So I'm mentioning this here. It's a little bit out of context over here, but it's very important that there are certain classical concepts that gained importance after the development of quantum mechanics. Okay. So you see, there is a lot of so the way of thinking about quantum systems and quantum mechanics is very different from the classical system, and it's only with time that you sort of grow to accept it. If you think too deeply about quantum mechanics at this moment, well, I encourage you to do so, but you will see that you get more and more confused rather than understanding more. However, with time, as you see how useful it is and you look at the applications and how everything works out, you start to believe in it in a way. You should, and the really strange parts of it, they start seeming less strange. Okay? And here, what I personally felt was that since we as humans, we are not, we're limited by our perception and our faculties. So there may be things which are outside our perception, and we have to sort of project them onto what we understand before we can use them. So quantum mechanics is something like this. It may, in principle, it may appear strange and unbelievable, but if you see that it works, you have to put your logical mind to it and say, okay, if it works, it must be true. It's something like this. So now let's go back again in time and see how humans actually came up with this probabilistic picture and things collapsing into eigenstates and not knowing what velocity something has, of a particle has. So why did they come up with this in the first place? So the story starts in 1814 with Fraunhofer, who observed the solar line spectrum. So if you so you remember, I guess, that a line spectrum can only come from quantized energy levels. So you've studied this at school with the Bohr's model, that if you did not have discrete energy levels, you would have a continuous spectrum, not a line spectrum. So the first recorded experimental evidence of quantization was by Fraunhofer in 1814. That is almost 100 years ago, before the term quantum mechanics was developed. It was not explained, but it was just an observation. And then 5 years later, Dulong and Petit, they were studying something quite different, the specific heat capacity of atomic solids. and they saw that the low temperature behavior of the specific heat capacity, it could not be explained by any classical theory. But that was that. There was no attempt at developing any theory. Then a long time passed, 40 years later, 1859, Kirchhoff suggested that the line spectrum of any material, whether it's the absorption or the emission spectrum, it can act as the fingerprint of a substance. So he was very smart. He found the use of the line spectrum, that it is very distinct to the material. But again, no one knew why the line spectrum is seen in the first place. Then 1 year later, Kirchhoff again recorded the black body spectrum. So this turned out to be the most important experiment on which quantization was developed. But in 1860, when he actually recorded it, I do not know if he realized how important it would turn out to be. But what happened was that this spectrum, the experimental plot of the variation of intensity of emitted light with frequency or wavelength, this could not be explained by classical theory, and it sparked the theorists into trying to explain it. This was in 1860. Then in 1885, Balmer followed up with the Balmer series of hydrogen. And in 1887 came the next very important experiment by Hertz, which was the photoelectric effect. So what he observed was that when you shine light on metals, electrons are emitted. Okay? So this was another crucial experiment. So there's the black body spectrum and there's the photoelectric effect. So these two turned out to be very critical. Then in 1888, so the E's in brackets are experiments, and if it's T, then it's theory. And in 1888, Rydberg made a formula for all the series of lines of hydrogen in the hydrogen emission spectrum. But this was from observation of experimental spectrum. So this is what is called an empirical formula. It did not, so this was an empirical formula. So it was not based in principles of physics. It was from experimental observation. And then 7 years later, Röntgen discovered X-rays, so, and including characteristic X-rays, which are sudden, like some frequencies show much higher intensities. He discovered X-rays. But no one was making any attempt to explain this note for almost now 80 years. Then in 1896, Zeeman observed the splitting of spectral lines under magnetic fields. You will come across this time and again. This is called Zeeman effect. So when you place an atom or molecule in a magnetic field, then the spectral lines split because of the interaction of the electron spin mostly with the magnetic field. So now almost 90 years have passed and people have made a lot of interesting observations. Then in 1900, Planck, in trying to explain the black body spectrum, came up with the first innovation in concept. So what he said was that if you quantize the energies of the emitted black body radiation, then you can theoretically explain the black body spectrum. So this was the first important theoretical innovation and introduced the concept of quantization of energy. Okay, but this is still a very preliminary stage. So he only introduced it in a, I should say he suggested it. The implications were still not evident. Okay. But it got the theorists up and running and saying, oh wow, this is a new thing. So it makes a lot of difference where if I say that only certain frequencies of radiation can be emitted, rather than saying everything can be emitted with different intensities. It makes such a big difference that it changes the behavior, it changes the full nature of the spectrum. Just this fact that you're not allowing all frequencies to be emitted. And from this idea, subsequent theorists, primarily Einstein in the first place, they came up with the whole of quantum mechanics. So this was 1900. This is a very, very important year for quantum mechanics. Then 2 years later, Leonard, he went back to the photoelectric effect experiment. So remember, it was observed in 1887 by Hertz. Then about 15 years later, yeah, if I'm calculating correctly, then he revisited the experiment and he made further observations, such as how frequency controls the photo emission of electrons, the frequency of incident light. Okay. And the detailed observations that he made helped Einstein in coming up with the concept of quantization of the energy of light. So this is again a very, very important year, and this is what Einstein got the Nobel Prize for. It is the quantization of the energy of light. So what Planck had said was that light is only light of certain frequencies are emitted. So this was quantization of emission of light. Einstein went a step further and he said the energy of light itself is quantized, which means that he introduced the concept of photons. Okay? And once he made this suggestion, he could explain all the observations that Leonard made in the photoelectric effect. So this theory gained quite easy acceptance. Okay? It was not a problem to accept this for people. Then he used this same concept of quantization of energy now to come up with the explanation for the low temperature behavior of the specific heat of atomic solids. So this was one of the very first observations by Dulong and Petit, which could not be explained by classical theory, remember. So Einstein revisited it with this enlightened idea of quantization of light or energy, and he explained it theoretically. So now you see the theoretical machinery is slowly developing. Simultaneously, there were a separate group of scientists who were looking at atomic structure, and they made certain crucial developments. So Rutherford, Geiger, and Marsden, this is a very well-known experiment, did the gold foil experiment on atomic structure in 1909. Okay. And then this was followed 2 years later by Mulliken's oil drop experiment, which determined the charge of the electron. And simultaneously, the discovery of particles was also going on, the fact that there are electrons and protons and neutrons. So they were also going on simultaneously. So the atomic structure was undergoing a huge upheaval during this time when Einstein was also proposing his concept of quantization, and everything sort of fell in place after a point, you'll see. And then in 1912, Planck, who had made the first crucial step of quantization, he also came up with the concept of zero-point energy, the fact that you cannot reach 0 Kelvin because of vibrations. Then there was quickly a lot of developments, both theoretical and experimental. Bohr proposed his model of the atom. Then the Stark effect was discovered, which is the splitting of spectral lines under electric fields. Then Frank and Hertz did an experiment on the quantum nature of atoms. So this was a sort of verification experiment of all the proposals that were coming in from other scientists. And in 1916, Einstein came up with the next crucial theoretical development, which was the quantization. Which was the quantization of momentum of light. So before he had said that the energy of light was quantized, so you have photons, and then he came up with the quantization of momentum of light. And this, and this became the fundamental equation which led to wave-particle duality. One of them, of course, there was another one. Then in the same year, so now everything is going quickly after 100 years. Sommerfeld and Bohr suggested elliptical electronic orbits in atoms. So Bohr had said circular orbits, remember? Then Sommerfeld came up with the idea of elliptical orbits. And when they suggested elliptical orbits, they could explain the Zeeman effect. Okay? And they also introduced the quantization of angular momentum of atoms. So with time, more and more things are turning out to be quantized. Okay? Then in 1920, Bohr, Sommerfeld, and Wilson, they together came up with a quantization rule. So this was this followed their elliptical orbit model, Sommerfeld's model, and this was related to the quantization mostly of angular momentum. So they made some rules, okay, using a theoretical basis, but also observation from experiments. And this is what is called old quantum mechanics. Old quantum mechanics. This basically involved mostly just the concept of quantization. All this probabilistic picture, uncertainty, these have not come in yet. Then came the next important experimental observation. So that was 1922, Compton scattering. So Compton observed that the scattering of X-rays, which means basically deflection of X-rays by free electrons, this could not be explained using without using the concept of particle nature of photons. So the Compton's experiment verified that photons carry momentum. Okay. So this is what this means, is that it verified the particle nature of photons. So this was proposed by Einstein in 1916, remember. He said that light has momentum, and Compton proved this with X-rays. Then came the Stern-Gerlach experiment, which verified the quantization of angular momentum of particles. So at this point, experiments and theories are going hand in hand. So some things are predicted by theory, people design experiments to verify this. Some things are observed by experiment and they use the new theories to explain it. So here everything is going on together around between, say, early 1900s to 19, maybe 25, 30. Okay. Then de Broglie came up with the next revolutionary concept. So far everyone was dealing with the particle nature of light. Okay, from the point that Einstein had proposed the concept of photons. Then de Broglie extended it to matter. He said that there is quantization of momentum of matter. This is what? This is wave nature of particles. And he used his theory to explain things like electron scattering experiments or electron diffraction. But remember that electron diffraction has not been experimentally observed yet. He proposed this, okay? And taking the two together, the particle nature of light and the wave nature of matter, people started talking about wave-particle duality. This caused a lot of debate among scientists because they challenged the whole premise of classical mechanics. So in classical mechanics, matter and radiation were very, very distinct. They were treated differently, both mathematically as well as conceptually. And there was it was not possible to treat them together because they were so different. But de Broglie and Einstein, the two of them together, they came up with wave-particle duality. Then in 1924, Bose, so S.N. Bose, he came up entirely mathematically with a statistical law that governs bosons. So what can I say about bosons? So I believe, okay, if you have not heard of it, so fermions and bosons, all particles are either fermions or bosons depending on their spin. So spin half particles are fermions and integer spin particles are bosons. Photons are bosons, for example. Electrons are fermions, protons are fermions. Okay.
Ma'am, can you please just repeat what you have just said? Means that boson and that portion, I didn't get that.
Oh, okay. So I just want to tell you. So I'm not going into details, but fermions and bosons, they are two types of particles. So all subatomic particles, they are either fermions or bosons. And this distinction depends on their spin. So if they have half integral spins, so 1 by 2, 3 by 2, 5 by 2, etc., then they are fermions. If they have integral spins, 1, 2, 3, 4, then they are bosons. And examples would be protons, electrons, they are fermions. Photons are bosons. You can say the hydrogen atom is a boson if you want to. Okay. And the statistics that governs them, or the rules for their distribution among various energy levels, that is different depending upon whether they are fermions or bosons. And boson comes from Bose, S.N. Bose, who came up with the statistical law that governs bosons. Okay? So why am I? So this is a part mainly of statistical mechanics, but why I mention it here is because this law was able to explain Planck's law in terms of the statistics of bosons. Okay, and once he came up with this theoretical machinery, he predicted the Bose-Einstein condensate, which has been in the news, and the experimental observation got the team the Nobel Prize not so long ago. So this was another important development from India, from Kolkata, in fact. And then in 1925 came the next direct development for quantum theory. So Heisenberg, Born, and Jordan, they proposed the matrix mechanics, which is basically a mathematical framework for dealing with quantum theory. Okay. So what do I mean by this? So classical mechanics has the Newton's laws, right? You have the rules which tell you how velocity changes, what is related to what, how you can predict the energy of a particle. So you have that mathematical machinery, which is called Newtonian mechanics. But so far, you see, there have been isolated equations, such as the quantization of momentum and then de Broglie's equation. And you have people proposing concepts of quantization of energy, momentum, angular momentum, but they are not unified in a mathematical framework. So how do you describe a system where where there are quantum effects? You need some sort of notation, right? What eventually turned out, so the most accepted language today is wave functions, which we will talk about a lot. But before there was wave functions, there was matrix mechanics. So here they were trying to explain the systems in terms of matrices of various kinds. Okay, this was the first mathematical machinery for quantum theory in 1925. And then in the same year, Uhlenbeck and Gutschmidt postulated electron spin. So they suggested that electron has something called spin, which adds to its angular momentum. Then in 1926, so this is a mathematical framework, and then in 1926, Schrödinger came up with an alternative mathematical framework, which has caught on, that is wave mechanics for quantum theory. Okay. So matrix mechanics is one sort of mathematical framework for treating quantum systems. Wave mechanics is another. This was followed in the same year by Pauli, who suggested the Pauli exclusion principle, which means that two quantum particles with the same set of quantum numbers cannot be present in the same same energy state. That is the most general thing, which basically translates into two electrons in the same orbital must have opposite spin. This you are perfectly aware of and have been using all the time. And then in 1926, Epstein came up with the quantum explanation of the Stark effect. So what was the Stark effect? Remember, it was observed in when was it observed? It was observed in 1913, which is the splitting of spectral lines under the electric field. And from 1913, about 13 years later, quantum theory helped explain it. So now, more or less, you see all the experiments that were not explained before by classical mechanics have slowly been explained by one scientist or the other using quantum explanations. So there's matrix mechanics, wave mechanics. Now the next mathematical development was by Neumann, who in a set of papers or developments between 26 and 32, he laid a more mathematical foundation of quantum mechanics. So this is something you will come across time and again. So this is like, so he came up with how to talk about properties of a quantum system. So the concept of Hermitian operators, then Hilbert spaces, so the functional analysis of wave functions. So this is all very mathematical, but it lays the rigorous foundations of quantum mechanics. The more deeply you go into quantum mechanics, if you do research, the more you will have to deal with these mathematical concepts. Okay. Then in 1927, Heisenberg came up with his uncertainty principle. So this is what you start with when you learn quantum mechanics. When there is just a small introduction to quantum mechanics, you start with the Heisenberg uncertainty principle. But this came much later in the day, as you see, in 1927. So quantum mechanics started blooming from about 1900 or 1905, and about 20 years later came the uncertainty principle. And from this point onwards, the more strange part of quantum mechanics, the probabilistic picture and the uncertainty of knowing things about quantum systems, that started emerging. And once the Heisenberg uncertainty principle came into the picture, there was conflict between scientists. And the physical interpretation of quantum mechanics confused everyone. So there were many alternative schools of thought. They argued about each other. Most people challenged it. Some people tried to explain it. In fact, Einstein, who started one of the founding fathers of quantum mechanics, he himself was not happy with the concept of uncertainty and probability. So he spent the rest of his life trying to disprove it in a way. So we'll talk about that. But before that, let's see how these people tried to convince the others that quantum mechanics is real. So in 1927, after Heisenberg came up with his uncertainty principle, there was a conference in Copenhagen. So this is a picture from the conference in Copenhagen. It involved all the major theoretical scientists at the time. And they tried to come up with a physical interpretation of what their equations were telling them. At this point, the fact that quantum mechanics could do a lot was obvious. It explained all the things that were not possible with classical mechanics. Okay, the equations were working fine. If you did experiments to verify them, they were doing fine. But what did it mean for, let's say, particle behavior or the reality of particles and waves? So this was almost at the borderline of science and philosophy, and this caused a lot of conflict. And in Copenhagen, they tried to resolve this. Like, what does it really imply? And the consensus eventually, well, not 100% consensus, but what came out of this conference was the probabilistic nature of wave functions. Okay, so wave functions is what was proposed by Schrödinger, and in terms of that, they came up with the fact that if you have quantum nature of particles, if you accept that and you use the mathematical machinery developed by Schrödinger and Heisenberg, whether it's matrix mechanics or wave mechanics, you have a probabilistic nature coming out, and that is the interpretation that fits with the theory and experiments that have been done so far. Okay, so this is what they came up with. Einstein, who is right at the center in the picture, he of course did not agree with this. He did well. Let's see. Okay, I'll tell you about a little bit later, because he came up with his arguments a little bit later, but he did not agree at that point. But the three main proponents were, like I mentioned here, was Bohr and Heisenberg, supported by Schrödinger. Okay. So Bohr and Heisenberg officially accepted what is called the Copenhagen Interpretation. And on the side, the same year, de Broglie's theory of wave nature of particles was verified by the electron diffraction experiment by Davison, Germer, and Thomson. And these are some pictures, presumably from the conference, where you see Einstein looks quite unhappy with Bohr, and they are discussing this Copenhagen interpretation, I guess, when the photo was taken, and Einstein did not want to agree with that. And here you have again Bohr. The man in the tie is Heisenberg, the black tie, and the other third person whose face you cannot see is Pauli. So I guess this was a very, very exciting conference. And then quantum mechanics just went from strength to strength after this. So the subset of scientists who accepted this formulation, they went ahead with more detailed studies. So Dirac in the same year came up with the equation for the relativistic electron. So he introduced relativity into the quantum equation for a free electron. Why was this important? So when you have small particles traveling at high speeds, this is a perfect case for relativity to creep in. So this is very important. So Dirac made his equation for the relativistic electron. Then in the same year, Darwin and Gordon, they extended this Dirac equation for a free electron to interacting electrons, so a many electron system, and they solved it for a Coulomb's potential. And then chemists, as you know, they want to apply these theories. So the physicists went ahead with their more and more details of the equations and more physical interactions, etc. So they kept developing the equations. The chemists, they went ahead with applications. So Hitler, he came up with the theory of the covalent bond from Schrödinger equation. So as soon as this wave function was understood, it started being used in chemistry. So he came up with the theory of the covalent bond. Then in the very same year, Hund and Mulliken, he came up with the molecular orbital theory. So this is the molecular orbital theory and the theory of the covalent bond. They are the bedrock of chemistry. And this is based on quantum mechanics. So even if you're just doing experiments with molecules, you cannot ignore quantum mechanics. It is there, whether you want to think about it or not, it's there. Okay? Then came Wigner, who related the degeneracies of quantum states to irreducible representations of symmetry groups. So this sounds like a very confusing statement if you've not done some group theory, but so basically he used symmetry arguments to tell us what states are degenerate. Degenerate means states with same energy. Okay. More or less fancy way of saying that the states have same energy. But all this was, so this is all in 1927, the same year as the conference. And then in 1935, it became important to explain to the general public what this huge discovery or discovery in physics and chemistry means. So this sort of public relations exercise was being done by a lot of people, and the famous Schrödinger's cat thought experiment was developed in 1935. Then in 1936, so I know this is a huge history. I'm sorry, it might get a little bit boring, but you just listen to it and you will realize how it's still relevant today. Okay? Then in 1936, Birkhoff and Neumann came up with quantum logic. So this is the So this is the sort of start of quantum computers. This is 1936, a long time ago, when quantum mechanics itself is on shaky ground. Neumann came up with the theory of quantum logic. Okay? And this is what has importance in quantum computers today. So you are basically living in the age of quantum computers, and during your career sometime, I believe, quantum computers will become a mainstream thing. And remember that it all started in 1936, not more than, maybe at that point it will be 100 years ago. And Then there was Jahn-Teller effect. You've heard of it in inorganic chemistry, without a single equation, I believe, but its basis is in hardcore quantum mechanics. It is the spontaneous symmetry breaking of nonlinear degenerate states. So when you have complexes, symmetric complexes, they spontaneously break their symmetry and lower their energy. If you want to explain this from the principles of, like fundamental principles, you have to go via quite rigorous quantum mechanics, in fact. Okay. Then, like I said, physicists continued with their exploration of fundamental interactions, and in 46 to 48, Rabi, Lamb, and Kush, they revealed discrepancies in the Dirac theory. So they did an experiment which showed that energy levels which were predicted to be degenerate by, the degenerate meaning same energy, by Dirac's theory were not actually of the same energy. Okay? And this difference in energy was called the Lamb shift. Okay? And this discovery again stimulated the development of electrodynamics, or Feynman's fundamental work later on. Okay. Quantum electrodynamics. So again, experiment preceded theory. So whenever you have an observation which does not fit with existing knowledge, your knowledge expands theoretically as well, because you have to come up with new concepts. Okay. Then in 48, Feynman made the path integral formulation of quantum mechanics. And the same year he made quantum electrodynamics. So you see, as soon as there was a problem, there are always smart people to come up with a solution. So in this very same year, or more or less between 46 and 48, Feynman came up with quantum electrodynamics, and it explained the discrepancies in Dirac's theory. So it explained the Lamb shift. And chemists, they are also going on with their work. So they observed NMR, nuclear magnetic resonance, in 1949. Okay. And NMR, of course, is in every chemistry research institute, and most chemists cannot do without it even for a day. So applications have also started, molecular orbital theory, NMR, everything, around the middle of the 20th century. So about between 1925 and 1950, let's say. Then in 1949, same year, this is in a different direction again, that magnetic fields affect quantum properties of electron forbidden by classical physics. So this was something that was observed by Ehrenberg and Seide. So these are again probing the fundamental properties of quantum particles. And in 1957, there is the many worlds interpretation of quantum mechanics. This is something I want you to Google and read about. I will not tell you exactly what it is. So this is an alternative to the Copenhagen interpretation of the probabilistic wave function. Google it, it's very interesting. It is not useful from a scientific sense, but it is a very interesting concept with a lot of philosophical interpretation. Then in 1957, Bardeen, Cooper, and Schaefer, we came up with the explanation for zero electrical resistance of superconductors. So I guess you directly see what this implies. This is this concept of superconductivity itself. They came up with it in 1957. And it's already in technology now, so you can see that it's important. So I'll give you a 5-minute break now. We've reached 50. I'll give you a break now, and then I'll just go through the rest quickly. Okay, it's a long history. It's a history of 120 years, and lots of steps there. And I guess you will realize that in 120 days, you cannot really cover everything. but we will just go with the bare minimum. Okay. Is it possible to pause the recording?
No, ma'am. Then new recording will have to be started.
Yeah,
Okay,
we will
okay,
have
then
to
let
start
it
a
be.
new
Let
recording.
it be. Let it be. Let it be. If you all have any questions so far, you can ask me now if you like. And drink some water or something.
Ma'am, which one do you prefer, ma'am? Copenhagen or many worlds?
I prefer Copenhagen. So the Copenhagen interpretation is a more or less scientific explanation. The many worlds, like I said, it's more philosophical.
So, ma'am, how do you think that when does the quantum particles then collapse to give us that our reality? If you are signing in Copenhagen, what do you think? At what point?
So what I think is that we are limited by what we can observe. Okay, so we cannot observe without disturbing. That is what we have been taught, right? But when I talk about wave-particle duality, I'll give you an alternative explanation. That it's not really that. I mean, it's not that
Yes,
you're
ma'am.
disturbing the system.
Ma'am, I know that in every wave system there can be this duality, this uncertainty in that. I saw something.
Yeah. Everything. There is an
Yeah.
uncertainty in everything. So everything is fluctuating. It's just that the probability about which it is, or the value about which it is oscillating, that is like the peak is narrower for large objects and heavy objects, and it is wider for small particles, which is why with small particles you can observe the uncertainty. I'll make it a little bit more clear. So if you're doing an observation on the quantum state of an electron, okay, and let's say you can have 5 answers, like there are 5 values that you observe, then maybe you observe the middle value and you take 10 observations. Maybe the middle value you get 5 times, and then some other values you get 2 times, 3 times, and 1 time. Okay, let's say the distribution is like this if you've done 10 observations. But if you're making an observation on something big, like let's say a chair, then you get the average value all 10 times. So you get the middle value all 10 times. So that it would make it seem that your observation on the chair is deterministic. So it definitely has that value because you didn't get any other value. But that's not quite true. If you increase the number of observations to, let's say, 1 million, you might end up with 2 or 3 other observed values. So the difference is like this. There is a probability picture for everything, but how easily you observe it is different. That is the difference between what we call quantum particles and classical particles. So there's nothing called, it's not a distinction. I mean, everything is quantum. Just that it's not easy to observe it if something is big. Okay, so that is the part, that was an obvious part. What is more difficult to accept is the fact that observing it collapses it into one of these states. So what quantum mechanics says is that if something is not in one of the states, so if something is, let's say, okay, let me say it like this. So the fact that you're getting multiple answers from the same system means that it is not definitely the reality is not any of these values, right? So it must be simultaneously in all these values, so that when you observe, you get one of them. So that is the part people find difficult to accept. That something is in multiple states, and then as soon as I observe it, it gives you one answer. But once you have observed that system, if you keep repeating it on that itself, then you'll get the same answer. Okay. So when I was talking about different observations, what I was basically doing is I'm making copies of the same system and then taking observations on each of them. If it was exactly the same system, so I have only one electron in my hand and I make an observation on it, then whatever value I get, if I do a third, fourth, fifth measurement, I will keep getting that value, which means that the system has collapsed into that state. But if before I made an observation, I made several copies, like 10 copies, and I made 10 observations on these copies, then I would get a probability distribution. So this difference is what confused people, and it still confuses people. I mean, it's not something we readily accept, because then the question automatically arises in your mind that then what was the state of the system? Okay. So the idea, so what quantum mechanics proposes is that it was in a superposition of states. That is the term that is used. That it is fluctuating between states. And then why it collapses, that question is answered by saying that when you make an observation, you disturb it. So that is what. So that is the sort of most accepted explanation for why it collapses into a given state. But this fact, you can have a more philosophical thing in this many worlds interpretation. But that is a bit more strange and it doesn't really help you, so it's not popular among scientists. The many worlds interpretation is pretty popular among philosophers and even lay people who are interested in quantum phenomena. Okay, so we
Ma'am, can I ask a
yeah.
question?
Yeah, sure.
Ma'am, why wasn't it felt that instead of developing a new theory, that it is probably just our instruments that are not good enough and we should aim to make better instruments? I mean, that seems
No,
more
so
plausible, right?
Yeah, of course, that seems more plausible, but it's definitely not the case because so the thing is that if you're just talking about the Heisenberg uncertainty principle, then this is a very obvious thing that comes to your mind, that our instruments are not good enough. Okay, but once you accept the probabilistic picture, then you're able to explain all the other observations, Compton scattering, black body radiation, etc., which had nothing to do with making observations. So the probabilistic picture is true in that context. Okay, that it can explain a wide range of phenomena with the same theory. The uncertainty principle, the development, it's not related to any sort of experiment. So it's even if you're not making an observation, the uncertainty principle is built into your wave function, and this wave function can explain a range of phenomena. If you don't accept the uncertainty principle, let's say it's a problem with your experiments. I'm not trying to explain an experimental observation. Okay, I'm just trying to develop a wave function, and you don't use the uncertainty principle. You say that everything is known. Then you go back to your classical equations, which were unable to explain anything. Okay, so it's not. It's definitely not the instrument.
Okay, so it does not have to do anything with the measurements per se. I mean, it may or may
No,
not be, right?
no, it doesn't have anything to do with an actual measurement. Even if you do thought experiments, so a lot of Einstein's work in trying to disprove this sort of probabilistic picture, he talked about thought experiments. Okay. And he tried to disprove it. But later it was shown that these thought experiments are flawed in a more mathematical sense. So that is the next thing I'll talk about now. So maybe that explains the things a little bit. So let's see. So this is post 1959. A lot of people started thinking about this problem. Okay, again, about what it implies, the concept of collapsing into eigenstates. And because Einstein, a very, very famous and well-respected scientist by that point, was opposing it, a lot of effort went into proving it as well. Okay. So the first, so in 1951 to 53, 1959 to 1961, those are a little bit different. I'll just go through them quickly. So there's the Orlov-Bohm experiment, which is how a magnetic field affects the quantum properties of an electron in a way that is forbidden by classical physics. So it tells you something about phases of wave functions, okay? About certain complex parts of the wave function which do not have any physical importance, but it can lead to observable changes. So that seems okay. It's a little bit vague, but anyhow. And then 1960, and there was an experiment which confirmed the theory that they proposed in 59. And then in 1961, Johnson did the second experiment, which proved the wave nature of electrons by doing a double slit interference experiment. So remember, there was the electron diffraction experiment before, and then there was in 1961 the double slit interference experiment. So electrons definitely have wave properties. Now I'm coming to what we were talking about before. So you may have heard of the EPR paradox, Einstein, Podolsky, Rosenfeld. Yeah, they had proposed certain paradoxes. What is a paradox? A paradox is a logical conflict about this concept of superposition of states and the eventual collapse into an eigenstate. So they had, so they did not believe that this sort of superposition of states can exist, and their logic was that if you have two particles which are coupled or in a way, let's say this is called quantum entanglement. So let's say you have two electrons of opposite spin or something, okay, and they definitely have to be of opposite spin because they're in the same state. And then if you move them physically apart by a very, very large distance, then if I make a measurement on one of the particles, then how will the other one know that I have done this measurement, and accordingly it would also become, so it would also have to change its state. So if you have, I have a pair of electrons, okay, let's say, and they are in a superposition of states of plus half, minus half, but which is which we do not know. This is the concept of superposition. So maybe electron 1 is plus half, electron 2 is minus half, or electron 1 is minus half, and electron 2 is plus. So if you make separate measurements on each of these electrons, you have equal probability of getting plus half and minus half. So their logic was that if I split them physically by a large distance and I make a measurement on one of them, then the fact that I have made a made a measurement that information must travel to the other electron if it is to adjust accordingly. Because if I make a measurement of plus half on electron 1, then the second electron must be minus half. Okay? So that also has to collapse into its eigenstate. But how is this information traveling if I have separated it by a huge distance? So they did not accept this because they said that if information has to travel, it has to be the fastest that the information can travel is at the speed of light. And then also there will be a delay in this information being transferred. And also the fact that this information is being transferred means that there is some sort of mechanism in the middle. Okay? So they did not believe that it could happen instantaneously or it could be a fundamental property of the system. And they proposed that there must be some local variables which tell you which electron is plus half and which electron is minus half. Maybe we do not know about it. Okay, maybe it's a limitation of human knowledge, but it is there. So that is what the EPR paradox, well, roughly was. Okay, there are more aspects to it. But then Bell in 1964, he came up with a mathematical sort of framework to explain this. Okay. And he said that, and well, he put this into a mathematical concept and he came up with certain inequalities or equations which could be experimentally verified. Okay. So he said that if just a minute. So he said that that if you that there were some constraints among the two particles, so mathematical constraints, and if you did certain specific experiments, you could verify if these inequalities or constraints were true or not. Okay. He proposed this sort of mathematical tool for verifying the EPR paradox. Fine. And then I'll skip this in between for some time. That in 1980 and 82, Alain Aspect, he performed this experiment that was proposed theoretically by Bell. And he found that his observations were consistent with the concept of quantum entanglement and not with Einstein's local variable theory. Okay. So he verified that indeed a superposition of states do exist. Okay. We may not know how they communicate, but the concept of superposition and quantum entanglement is correct. So this was Alain Aspect. And then, of course, you see, it's still difficult to believe. So there were people who did not still accept the experiment. So, but in 1986, Tonomura, he made a more conclusive proof of the Aronoff-Bohm effect. So this was also related to the Bell's theorem. And so together, so Alain Aspect's experiment was a more direct verification, but with Tonomura and others as well, eventually it was accepted that the superposition of states is the correct explanation, and Einstein's local variable theory was discarded. So this involves a lot of reading and understanding and confusion. So I cannot do this in 5 minutes. In fact, I myself am not entirely comfortable with the whole thing, but this is how it evolved, and then the superposition of states was accepted widely. Okay. Then simultaneously, developments in quantum entanglement and led to the development of quantum computers. This is where I would like to end today, because you see they're in the news all the time now. So between 1969 and 77, the quantum theories for electronic switching and memory devices in computers were developed by Mott, Anderson, and Van Vleck. And these are already in use in classical computers. Then Benioff and Feynman. So this is the start of, or proposal for, quantum computers. Okay. So Benioff and Feynman, they gave the first theoretical description of a quantum mechanical computer. So a quantum computer. And this is sort of living proof of the fact that the concept of quantum entanglement is now accepted. People are spending money to develop millions and billions of dollars to develop these quantum computers, and they're working.
Google and NASA also collaborated and developed the quantum computer.
Yes, yes. So Google, IBM, there are several startups. Quantum computers are actually accessible, like real quantum computers through IBM. So they're already there, several of them. Okay, so they're working. So this is conclusive proof that quantum entanglement is definitely true. So there's no reason to not believe it. But yeah. So this was this all started in 1980. I was not aware of the existence of the proposal for quantum computers till they started being produced, but you see it takes a long time then, from 1980 to 40 years now. Then there was someone from Kolkata again, Chakraborty from Essenbo Center, I believe, who made a very important contribution to quantum computing. He showed the effectiveness of quantum annealing over classical simulated annealing. Now, what is annealing? This is a fancy way of saying optimization. Okay. There are little bits of differences, but that's okay. I mean, we are not quantum computer specialists. So he showed theoretically that a quantum optimization algorithm would be better than a classical algorithm. And then in between, there was this fantastic development that Cornell, Wyman, and Ketterle, they experimentally observed the first Bose-Einstein condensate, leading to the Nobel Prize that they got. And then in 1998, a quantum algorithm was demonstrated for the first time. I'm not sure, I believe this is not on a quantum computer. This will be on what is called a simulator, a classical simulator for a quantum computer. Okay. Then in 1998, Chakraborty's work was verified when the quantum annealing was showed to be better than classical simulated annealing. And something very interesting happened in 2004 when a quantum entanglement was experimentally demonstrated for the first time between trapped calcium ions. So this was called teleportation. So if you've seen Star Trek, you know that they teleport between planets and starships. So this was something similar, that the state of one calcium ion was teleported to the other one. Very interesting. In 2005, the first quantum byte was created, the qubite. So that's 8 qubits. 8 qubits? I'm not sure. Okay, don't take my word for 8. May not be. Okay. Then quantum copying. So if you want to have a quantum computer, you will need to copy things. You have to be able to do that. So this was demonstrated in 2005 in Harvard University. Then in 2009, there was the first quantum computer. Then in the same year, so this was by one scientist, O'Connell. Then the Boulder University as a team, they made the first universal programmable quantum computer. Again, that is an important thing. You also need to be able to program a computer for it to be useful. And after that, in quick succession, the size of the quantum computers and the technology used to make them, that has been improving. So there was, in 2017, there were 4 companies who developed it, D-Wave, Microwave, Intel, and IBM. 2018, there was Google. 2019, IBM made a big quantum computer. Okay. And in 2019, so just 2 years ago, there was a very remarkable but unpopularized change in the definition of the kilogram. So earlier it used to be just a block of material in Paris.
Now they fixed it on the physical constant, the fundamental constant.
Yes, now they're defined.
The fixed value of mole, I think.
Yeah, so it was sort of redefined so that it's not dependent on anything physical in 2019. And then in the same year, there was an actual photo of quantum entanglement.
And how will you take the photo of quantum entanglement?
You can Google it. You can see the photo if you want. So they could photograph the system. So quantum before 2019. So once this calcium thing was done, after that many people have generated these entangled systems. So in a quantum computer also, basically it's entanglement of all these qubits that is used to record information and manipulate information. So it's very, very real.
Yes,
How they took the photo?
I know that, but how will you photograph that? I mean, entangled photons and photographs you take from light, and that is also photons. So how will that work?
How you have taken, well, I really don't know how he has taken the photograph, but so let's see. I will Google it for you and tell you exactly. So just 1 minute. I'm not sure how he photographed it really. So he proposed, okay. They used lasers and crystals apparently. They took a photo of entangled photons. And then they hit a crystal with an UV laser, and then those photons from the laser broke into 2 photons. And then they collected these as a photograph. They snapped a picture using a special camera that could detect individual photons, but only took a photo when a photon arrived with its entangled partner. So so because these were entangled photons, I think they could manage, because if there were other things and you put a photon on it, it would collapse again. So these were entangled photons which helped them to do this. So that's it. So last 2 years, you can get yourselves up to date if you like. So I will stop at 2019.
Ma'am, due to COVID, then it was, is it reduced or what?
What? Due to COVID, what?
Yeah, ma'am, I was saying, so ma'am, there is nothing for 2020. So was there something and you just stopped, or was due to COVID some...
Oh, no. I didn't have time to look for what exactly happened in 2020. So
because COVID stopped everything, we are stuck at home.
No, it's not that. I mean, so I made this timeline by researching a lot, but I didn't have time to do it for 2020. So then, of course, if you go in the field of quantum computation, has been huge developments in the last year. So, but that is, I mean, I'm not going to teach quantum computation. I don't even know it properly myself. So don't want to burden you with so much. But I wanted to tell you that the field is moving in that direction so far. And it's not a dead field. If I just keep telling you things about 1800s and early 1900s, you might think, okay, this is a really, really old field, but it's not. That is what I wanted to emphasize, that everyone is still very much interested in it. Okay, and like I said, there's been 120 years of development so far, and our course is about 120 days. So we will have to stop at very old things. But if you continue, you will of course come all the way to today's research. It is so quantum physics, quantum chemistry, quantum optics, quantum computing, any field, everything is getting a quantum added to it currently. So there's an opportunity in many, many fields. So let me just stop here today. 2 hours is a very long time for a history lesson, but I hope you get a feeling for how the field developed, and we will try to follow the developments as far as possible. So next class is Thursday, 5 p.m. Right? Okay. So you can stop the recording.